gravity load, and on the right, the same frame has been subjected to lateral loading. The load has been applied at the beam level, which is a story level, and you can see we have discussed this in the previous lecture, that in the gravity load, bending moments are produced in the beam at mid-span with the tensile stresses occurring in the bottom portion of the beam, and tensile stresses produced in the upper part of the beam at the ends of the beam. When the same frame is subjected to earthquake loading, additional bending moments are produced both on the positive and negative side of the beam, but at the ends of the beam. Nothing happens at the midspan of the beam. Similarly, the additional bending moments are also produced at the ends of the column, and nothing happens at the mid-height of the column when a frame is subjected to lateral loading. The final effect of lateral loading will be additional bending moments produced at the ends of beam column joints, and then this frame must be designed for the combined effect of gravity and lateral loading. So the conclusion from this discussion was that whenever a frame, a reinforced concrete frame structure is subjected to lateral loading, bending moments are produced at beam column joints or the ends of the beams and columns. So then the columns must be then designed for the combined effect of requires some special provisions, and the ACI code has placed most strict provisions for SMRF. And while analyzing a special moment testing frame for earthquake loading, R factor is taken as 8.5, which further demands or requires that special moment testing frame must be analyzed, designed, and detailed in a special manner, so that when special moment testing frame undergoes several cycles of inelastic deformation, it should not collapse, and it should be able to get energy through cracking it, and the ends of the beam and columns shall be properly detailed so that it enables the energy dissipation to occur in an efficient manner. So SMRF is an efficient frame, and R factor for this is taken as 8.5. However, the AI code has placed very strict provisions for SMRF, as you will see in the next slides. Then IMRF is an intermediate moment testing frame. R factor is taken as 5.5, and it is a less efficient frame as compared to SMRF. Therefore, the provisions which ACI code has placed for IMRF are less strict than those for SMRF. OMRF is the ordinary moment testing frame with no special provisions being placed for ACI code. Okay. The SMRF is a special moment testing frame, and ACI code further requires that in the highest seismic zones, zone 3 and 4, only SMRF shall be used. In the intermediate seismic hazard zones of 2A and 2B, IMRF is allowed, although the code recommends to use SMRF, but IMRF is allowed as per the code requirement. In zone 1, OMRF is allowed, but again, the code encourages the designer to use IMRF or SMRF. Okay. Then we also said that there are some general requirements for all types of frames with the minimum concrete strength in all parts of the frame shall be at least 3000 psi, which is cylinder strength. There is no maximum limit on ordinary concrete. However, there is a maximum limit on lightweight concrete, and which is 5000 psi. Most designers would like to use lightweight concrete in their structures, because if structure is lightweight, then W, which will affect the base shear, the lighter structures would produce less base shear, and less base shear mean less forces at the story level, less stresses and less bending moments, and final effect of this will be an economical structure. However, as there is not enough data available on the use of high strength lightweight concrete, therefore the ACI code has placed a restriction on the use of lightweight concrete, and that restriction is with regard to the strength of concrete, that 5,000 psi is the maximum limit for lightweight concrete. With regard to the steel, if grade 6, if ASTM A706 steel is used, then grade 60 steel can be used without any further requirements, because ASTM A706 is a very good quality steel with regard to its ductility. And it is a ductile steel, although it is a little bit expensive, and it is produced only by few factories in Pakistan. Only recently they have started its production. When ASTM A615 is to be used in the members of a movement testing frame, then either grade 40 or 60 can be used. However, there are two requirements. If a ASTM A615 is used in the members of movement testing frame, and these requirements are: number one, that actual yield minus the specified yield shall not differ by more than 18 KSI, which means that if you take a sample, of steel from the yard where the steel is stored at the site, test it in the lab, and you get your actual yield from the test, and then actual yield minus the specified yield, which for will 40 and 60, but not more than 18 KSI. As an example, let's say you bring a steel sample from the field, which is grade 40, you test it, and the actual yield comes out to be, let's say, 65. Then actual yield is 65 minus specified yield, which is 40. So 65 minus 40 is 25. 25 is not less than 18 KSI, it is more than 18 KSI. So this steel shall not be used in the members of the movement testing frame, any member of the movement testing frame. There is another requirement, and that is when actual ultimate is obtained from a test in the lab on a steel sample from the yard at the site, then the ratio of actual ultimate to actual yield shall not be less than 1.25, it shall be more than 1.25, which means that actual ultimate strength shall be 25% more than the actual yield. These two requirements are meant to ensure that there is enough gap between strength and ultimate strength, so that there is enough reserve strength in the steel, because this reserve strength is basically responsible for ductility of the steel. As you know that strain ductility is defined as strain at ultimate, the strain at yield. So if a strain at ultimate and strain at yield are very close to each other, then the strain ductility will be less, and the steel will not be able to undergo cycles of inelastic deformation, and it can break, and the breakage of the steel can cause collapse of the steel. Okay, then we also said that the regions where there is the critical regions, both in beams and columns, shall be properly confined so that they are able to undergo inelastic deformation without collapse. And this confinement can be produced by using stirrups, cross ties, and hoops or continuous ties. And they help in three ways. Number one, they will carry the horizontal shear forces. In a gravity load, usually the column would not be subjected to any shear forces. However, to lateral load, then shear forces, horizontal shear force will be produced in the columns, and the columns must be designed against these shear forces. So whenever ties are provided in columns, they will resist these horizontal shear forces. So this is one action. One way these ties will help the columns against horizontal shear force. The way these ties and strips will is that they hold together the vertical bar and prevent them from excessive bending and outwards. In technical terms, this bending phenomena is called buckling. So this is the ultimate stage where the concrete would have already cracked severely, and of the concrete portion would have already occurred. And when this happens, bond between steel and concrete would have broken. And after bond between steel and concrete breaks, steel alone at some stage has to transfer the load from the top floors to the bottom to the foundation. So when this happens, steel might buckle under the load, under the axial load. So for this purpose, these ties in the column will help in preventing buckling. This stage buckling of the steel bar, not buckling of the section. Buckling of the whole section or long or slender column is totally different from the buckling of the steel bar at this final stage of failure. In another way, the ties will help the column, and that is the confinement of the concrete. The concrete in the column will be subjected to several cycles of inelastic deformation. So the concrete is not properly confined by these ties, then they will come under the load very easily. So these ties will also help the confinement and by provided 135-degree hook, as you will see in the next slides. And these hooks are called as seismic hooks. Such hook ends, the ends of such hook will prevent opening of hoops, and consequently buckling of concrete and buckling of vertical bar will be prevented. Okay, then there are provisions now which are specifically meant for SMRF. And as you know that beams and columns are two members in a frame structure. Beam is a horizontal member and column is a vertical member. So when a beam and beams are not subjected to usually to axial loads, axial load on beams is significantly less than the axial load on the columns. Therefore, the ACI code, instead of saying that these provisions are meant for beams and these provisions are meant for columns, the ACI code has divided the two provisions based on the axial load to which a member is subjected in a frame structure. The ACI code says that whenever a member of a frame structure, which is SMRF specifically, now we are talking about special moment testing frame. If a member is part of SMRF, and if this member is subjected to an axial load, which is less than the AGFC prime divided by 10, then this member shall have the following are the provisions in the following slides shall meet the provisions in the coming slides. Okay. The AGFC prime is basically the axial load capacity. AG is the gross area of the member, and FC prime is the concrete strength. Divided by 10 means 10% of this axial load capacity. As an example, let's say there is a member in a reinforced concrete frame structure, either beam or column, whose cross-sectional area is 144 square inch, which means 12 by 12 inch member. NFC prime is, let's say, 3 KSI. So for this member, 144 multiplied by 3 KSI are 3 KSI multiplied by 144 is around 400 kip. 400 divided by 10 is 40 kip. So if axial load on this member is less than 40 kip, only then the provisions in the next slides will be applicable to that member. And as beams are subjected to axial loads quite less than what is being mentioned on this slide, so all these provisions are applicable to beams until unless there is a very special beam in a reinforced concrete frame structures which is subjected to axial load more than this. Then these provisions will not be applicable to beams. And on the other side, if there is a column in a very low rise structure and the load on the axial load on the column is less than AGFC prime by 10, then also these provisions will be applicable to those columns. Okay. And these provisions are, but generally speaking, to avoid any confusion, you should remember that these provisions are generally applicable to all beams in a reinforced frame structures. So if you do not understand the previous discussion, you should just remember that these provisions are applicable to beams. Our columns will be discussed after these provisions. So which means that if a beam is part of a reinforced concrete frame structure, and if this frame structure is treated as special moment testing frame, then this beam shall have these requirement. Number one is on the length to depth ratio. The beam is part of special moment testing frame shall have length to depth ratio of more than 4 or equal to 4. As an example, if a beam is only 15 feet long and if its effective depth is 16 inch, then length to depth ratio is 15 multiplied by 12 divided by 6 is 11.25, which is greater than 4, and this is okay. However, if the length of this beam is only 5 feet, then it will give us a ratio which will be less than 4, and that will not be desirable. Okay, and the reason for this is that ACI code wants to prevent the undesirable shear failure, because shear failure is brittle, and the favorable mode of flexure. So sure failure of failure. That's why the ACI code frame, then that will be at least 4 or more. The size of the beam, which is part of special moment testing frame, that the breadth to depth would be greater than or equal to 0.3. As an example, if width of the beam is 12 inch and depth is 18 inch, then B to H ratio is 0.67, which is greater than 0.3 in this case. Our beam is very deep, let's say, so 12 divided by 60 will give us a ratio which will be less than 0.3, and this will not be advisable size for the beam, which is part of special moment testing frame. The ACI code, this provision of the ACI code, by this provision of the ACI code wants to make sure that beam is not very slender along the depth of the beam, not along the length of the beam. Okay, finally, the width of the beam, which is part of the special moment testing frame, shall be at least 10 inches in order to avoid any condition of steel to be placed inside the beam. Okay, now on the reinforcement to be placed, provisions which are more or less similar to what you have already studied in the beam design, that minimum reinforcement according to the code shall be equal to 200 divided by 5 are this equation. You know these two equations you have studied. Maximum reinforcement for all grades is being placed equal to 0.025, which is 2.5% of the grass area of the beam. And this minimum 2 bars shall be placed at every location of the beams, at all sections of the beam. And generally happens in almost all beams that 2 top bars and 2 bottom bars are provided. So these are this provision is automatically satisfied. Okay. Over and above this, there are provisions for reinforcement, especially at the bottom of the beam, at the ends of the beams. Uh, if you remember, we now quite a few times we have said additional bending moments are produced in the beam column joints, which means at the ends of the beams and ends of the columns when a frame structure is subjected to earthquake loading. So, and these ends of the beams and ends of the columns will be subjected to a significant loading due to earthquake, significant bending moments, and significant stresses both at top and bottom of the beams. The ACI code wants to make sure that enough reinforcement is placed, especially on the positive side of the beam at the ends of the beams. Because usually, if you remember in the previous several example in the beams, we used to curtail beams because we used to curtail bottom bars in the beams because we said that bending moment is maximum at the midspan of the beam and bending moment decreases as we move towards the end of the beams. But as we have seen in one of the slides that we discussed in the beginning, that bending moments are also produced at the ends of the beams on the positive side of the beam if this frame is subjected to lateral loading. Therefore, whatever area of steel is calculated from the bending moments obtained from the combined effect of gravity and earthquake loading, that reinforcement must be checked against this reinforcement. And this reinforcement, this provision of the ACI code says that whatever area of steel has been calculated from the analysis shall not be less than 50% of the area of steel being placed on the top portion of the beam at the ends of the beam, which is the negative reinforcement. As an example, let's say from the analysis
अस्सलाम वालेकुम सर। क्लास है कि नहीं?
Okay. I hope you can hear me now, because there was an internet breakdown, which we lost connection of the internet. And before that, we were discussing the provisions of ACI code for beams, for those beams which are part of special moment testing frame. And we said that the ends of the beams must have some reinforcement on the positive side of the beam, at the ends of the beams, which shall be at least 50% of the negative reinforcement or top reinforcement at the end of the beam. And by this, the ACI code wants to make sure that both positive and negative side of the ends of the beams are efficient in energy dissipating, because if there is not enough longitudinal reinforcement on the positive side of the beam, at the ends of the beam, then the beam may fail in flexure at this location and causes premature collapse of the beam. Okay, the procedure for this is that when the analysis is completed and the bending moments, both from gravity load and lateral load, are added together, an area of steel is then calculated for the combined bending moment. After that, that area of steel on negative side will be placed as it comes from the analysis, but on the positive side, if area of steel calculated from the analysis is less than 50% of the area of steel being placed on the negative side, then it must be increased to 50% of the negative reinforcement. As an example, if 10 bars are required against bending moments obtained from gravity and quick loading on the top side of the beam, at the ends of the beam, then at least 5 bars must be placed on the bottom side of the beam at the same section. Whatever reinforcement is obtained, regardless of whatever reinforcement is obtained from the analysis. If the reinforcement obtained from the analysis on the positive side, bottom side of the beam, at the end of the beam, is more than 50% of the negative reinforcement, then that reinforcement must be placed. However, if it is less than 50% of the negative reinforcement, then the reinforcement shall be placed at least 50% of that reinforcement. Okay. And then there is another provision that at all section of the beam, the reinforcement, the reinforcing bars must be 25% of those placed at the ends of the beams on the negative reinforcement on the top side of the beam. As an example, if 10 bars are required on the negative side of the beam, at the ends of the beam, then 10 divided by 4, at least 2.5 bars, which means 2.5 rounded up to 3 bars must be used at all section in the beam, both top and bottom. Okay. Another provision for the ends of the beams, the ACI code has placed a restriction on the beam ends within a length from the face of the column to a length in the beam equal to twice the thickness of the beam, twice the depth of the beam. So within this location, the ACI code wants to use a stirrup with the provisions as mentioned in this slide. The stirrup spacing must be the least of these 4 requirements, the least of these 4. D means the effective depth of the beam divided by 4, 8 into smallest longitudinal bar diameter, and 24 into hoop bar diameter are 12 inch. Let's say the beam depth is effective depth is 16 inch, so 16 divided by 4 will be 4 inch. 8 into smallest longitudinal bar diameter. Let's say the smallest longitudinal bar diameter used in the beam is 6 by 8. So 6 by 8, this will give us 6 inches. 24 into hoop bar diameter. Let's say this is 3 by 8 bar. So 3 by 8, this will give us 3 by 8 multiplied by 24, 9 inch and 12 inch. So out of all these four requirements, the least is 4 inch. So we will use the stirrup spacing of 4 inch within this region, which is from the face of the column to a length equal to twice the depth of the beam, regardless of the stirrup reinforcement which is obtained from the analysis. But if the stirrup spacing is less than that obtained from the analysis, then that less spacing shall be used. It is only, this provision will only apply if stirrup spacing is more than the one obtained from the analysis. So if the analysis gives you less reinforcement, less spacing than this, then it will be okay. But if the analysis gives you more spacing than these four, the least of these four, then the least of these four spacing will be used here for stirrups. And by this provision, the ACI code wants to make sure, once again, to confine concrete in this area and to provide a kind of stiffness to this area so that this area is capable of undergoing an elastic deformation and cracking without any collapse. At any other location, the stirrup spacing shall be less than or equal to d by 2. And this must be checked against the analysis spacing. If the analysis spacing is less than this, then that will be okay. But if it is more than this, then this spacing shall be used. And this requirement is applicable to both ends of the beams and on both sides of the beam, on both sides of the column in the beam. There is another requirement on lapping. You know that very often you would require lap splicing by lapping of the steel bars, especially on the bottom side of the beam, because the beam reinforcement on the bottom side must be placed continuously from end to end. So if this lapping is required, then the lapping shall be provided within a region which is out of the critical region of the end of the beam, equal to twice the depth of the beam, and also away from the midspan of the beam. So this should be located in this region, which is away from the midspan as well as from the end of the beam on the bottom side. The yellow places shows those locations where lapping is prohibited on the bottom side. Okay, on the top side also, at the ends of the beam, the lapping is prohibited, but this is very easily achievable because the negative reinforcement is usually curtailed at location where it is no longer required. And the midspan of the beam, the negative reinforcement at the midspan of the beam, the lapping in the midspan of the beam on the top side of the beam for negative reinforcement is allowed. Lapping can be done at this location. The lapping will become challenging on the bottom side of the beam because it can not be done at the ends of the beam, nor it can be done at the midspan of the beam. So the placement of such lapping within the permitted locations will become a challenge in the field. Okay. And the stirrup spacing within this lap location shall be at least d by 4 or 4 inches. It cannot be more than 4 inches in any case. Similarly, the lap length shall be equal to 50 diameter of the bar for if CPM is equal to 3 ksi, Fy is equal to 40 ksi according to this equation, and 70 bar for if CPM is equal to 3 and Fy is equal to 60 ksi. Mechanical splicing, which can be obtained through some mechanical devices, is also allowed in the same locations where lap splicing is allowed. However, the mechanical splice shall develop in tension or compression is required at least 125% of the specified yield strength of the bar. And by this provision, the ACI code wants to make sure that steel yields before the mechanical device breaks, so that the breakage of the mechanical splice is avoided, in order to make sure that ductile failure occurs at those locations. The same provision applies to welded splices. Welded splices, welding is also allowed in those locations where lap and mechanical splicing is allowed. But again, a welded splice will also develop at least 125% of the specified yield strength, for the reason explained in the previous slide. Okay, then we have provisions for columns. If a column is part of pressure movement testing frame, then the size of the column shall be at least 12 inches, and the short to long side ratio shall be more than 0.4, which means that 12 by 12, 12 by 18, 12 by 24 columns are allowed, but 12 by 36 columns are not allowed. Again, by this provision, ACI code wants to make sure that the slenderness along one of the weak axes is avoided along the height of the column. Okay, minimum reinforcement, longitudinal reinforcement shall be 1%, maximum reinforcement 6%. However, practically, it would be very difficult even to place reinforcement more than 3% because of the congestion of steel in the lap locations. Just like beams, in the columns, there are also critical regions at the ends of the beams, both on top and bottom sides of the beam. This location in the column is defined by the length L0 against the location defined in the beam by 2h. So this L0 shall be the largest of H1 or H2, which is the size of the column, or clear span divided by 6 and 18 inch. As an example, let's say if a column is 12 by 18 inch, then largest of H1 12 inch or H2 18 inch is 18 inch. Clear span divided by 6. Let's say the column is 12 feet high, so 12 divided by 6, this will be 2 feet or 18 inch. The largest of this will be 2 feet, so L0 will be 2 feet. Within this 2 feet region, stirrup must be placed according to this requirement, which is 0.25 or deep or 1 by 4 multiplied by smaller of H1 or H2. 12 divided by 4 will be 3 inch. 18 divided by 4 will give us 4.5 inch. And 6 into longer bar diameter. Let's say the bar diameter is 1 inch, so it will be 6 inch. And S0, the least of this will be used. Okay, if from the analysis, if spacing comes out to be less than what is mentioned here, or what is obtained from these three, from the least of these three equations, then the analysis spacing shall be used. However, if the spacing from the analysis comes out to be more than this, then these provisions, the least of these three requirements, the spacing obtained from the least of these provisions shall be used as spacing in this L0 region. Okay, S0 will be explained in the next slide. Elsewhere, the spacing of 6 in longer diameter 6 inch is applicable. S0 is defined on this slide, and S0 is applicable to very long or very large column, large in size, along one of the directions specifically. So if a column is like rectangular, and if the column is such that it has too many longitudinal bars, then there is a code requirement that alternate bars must be engaged by cross ties, like shown in this slide. This is one bar. This is first bar on this column. Second bar need not to be engaged by cross tie or hoop, but the alternate. This one is alternate, and again this one is not needed to be engaged by the cross ties, but this again shall be engaged. The ACI code requires that every alternate longitudinal bar shall be engaged either by a cross tie or hook tie. So when this is done, then the distance between the alternate engaged bars is called as HX. Okay, and Then the S0 is the spacing vertical, the vertical spacing between the ties. S0 is vertical spacing between the ties, and HX is the horizontal spacing between the alternate cross ties. The S0, the vertical spacing between the ties, then shall be more than 4 inch and shall be equal to this equation, but not to be more than 6 inches. This equation is equal to 4 plus 14 minus hx divided by 3. Let's say hx is 14 inch. So 14 minus 14 will be 0. 0 divided by 3, this will be 4 inch. Okay. So with the increase in hx, this S0 spacing will decrease. So that if the distance between the alternate bar is more or the engaged bar is more, then the vertical distance is less. Vertical distance will decrease so that the location is properly confined. Okay. If hx is, let's say, 11 inch, then it will be 14 minus 11. 14 minus 11 divided by 3 and S0. So S0 will be slightly less than 4 inches. So S0 will be 4 inch to 6 inches, and the maximum value of hx cannot be more than 14 inches. So when this S0 is calculated, this shall be compared with this two equations from this slide, and the list shall be used in the vertical spacing for ties in the column in the region of L, in the region L0. Okay, if lap is required, which is usually the case, lapping will be required. Lap splicing is usually done in the columns. So if a column is part of special movement testing frame, then lapping is only allowed at the mid height of the column, and this also becomes a very challenging requirement of the ACI code, especially with regard to wastage of steel, because the steel bars are stocked and supplied in certain specified lengths, and to adjust those bars in the mid height of the column from the lengths already obtained from the factory, then it's quite possible that wastage is done. Some bars will be wasted. So slight adjustment is possible as per code requirements, but it will depend from situation. It will depend on particular situation. It will vary from situation to situation. So this, if lapping is done here at the mid height of the column, which is one of the requirements of the ACI code, then the spacing of the stirrup shall be at least d by 4 or 4. It cannot be more than 4 inch in any case. And lap length requirement is similar to the lap length requirement in the beam, 50 diameter of the bar and 70 diameter of the bar for 40 and 60 respectively. Okay, the joints of special movement testing frame also have some provisions. The light blue part is called as beam column joint, and the beam column connection is different from the beam column joint. Beam column connection extend into the beam and column up to the length in the beam equal to 2h on both sides of the column and up to a length of L0 on both sides of the beam. So L0 in the column from on the top side of the column from the beam, bottom side of the column from the beam, L0 in the column, and 2h on both sides of the column. This is called as beam column connection. However, joint is the common location to beam and column. If the joint fails, so the effect of the joint failure is more significant or more severe for the columns than the beams, because the axial load will be transferred through this joint to the bottom portion of the column and finally to the foundation. So if joint fails, then the load path will be disturbed. The axial load can be no longer transferred to the foundation if anything happens to the joint. Therefore, the ACI code requires provisions for the joints so that joint is properly confined and joint does not fail, or concrete in the joint does not significantly crack in the earthquake. So because if this happens, then the axial load path will be completely disturbed and the collapse of the structure can happen. These are some tests which we have done in our university. This was one of my PhD students who did some work on the beam column exterior joints. You can see cracking of the joint here. You can see the movement of the slip and movement of the concrete in the joint. Very visible. This is called inelastic deformation cycle or stress cycles. This is an interior joint. You can see an interior joint and it's subjected to lateral loading. There's a lot of stress cycles and activity happening within the joint. If the joint fails, then the vertical load path will be disturbed and the whole structure can collapse. Okay, keeping in view the importance of the joints in particular and the connection in general, the ACI code has developed a separate code for the design of connections, and the ACI code 318 contains few provisions for the beam column connection, but the detailed provisions are available in a separate code of the ACI. These few provisions which are part of the ACI 318 we will study, but the other provisions are in very detail, and we have one complete lecture on the design of connections in our MSc. If you want to study the design of connections in detail, you can download that lecture from the website. Okay, these requirements are specifically meant to make sure that if any hinge has to form after the cracking of concrete and yielding of steel, that the hinge shall form within the beam and not in the column, as I explained earlier. So this give rise to a concept which is very commonly known as weak beam strong column approach or weak beam strong column connection. So the beams must be weaker, the beam parts in the connection, this 2H part in the beam shall be weaker than the L0 part in the column, so that connection, if connection is to fail, then the failure shall initiate in the beam part rather than in the column part. Okay. And for this reason, the ACI code has placed a restriction that the column flexure capacity of the connection must be 20% greater than the beam flexure capacity, and the column ties shall be 135-degree hook and continue through the joint, as you will see in the next slides. Okay, this is just an explanation of the flexural capacity of the column, the collective flexural capacity of the column on the bottom and top of the column shall be greater than 25% of the beam top left and right. This MNCT means the moment, nominal moment of the column on the top side of the beam, and moment, nominal column, MNC column, nominal moment of the column on the bottom side of the column. This MNBR means the nominal moment capacity of the beam. B means beam on the right side of the beam. This is the left side MNB, and MNBL plus MNBR will give us collective bending moment capacity of the beam. MNCT plus MNCB will give us collective flexural capacity of the column. The collective capacity of the column, MNCT plus MNCB, this must be greater than 6/5, which is 20% of the collective capacity of the column, of the beam, sorry, MNBL plus MNBR. This is for the left side, this is for the right side. Okay, the bending moments, if the bending moment direction is reversed, so this will be the case. Anyway, this is just an explanation of the provision that the flexural capacity of the column at the connection shall be 20% more than the flexural capacity of the beam at the connection. Okay, this is again another provision, and according to this provision, the width of the joint, the width of this joint within the column As I said earlier, that although this portion is common to beam and column, the effect of the joint failure is more catastrophic for column than the beam, because if this joint fails, then the axial load capacity will be severely disturbed and may cause collapse of the whole structure. Therefore, the ACI code wants to make sure that this joint has enough width and this must have enough capacity. In order to make sure that this joint has enough width, the ACI code has placed a restriction that if the longitudinal bar diameter in the beam, is, let's say, 1 inch, then the width of the column, because the width of the joint is basically the width of the column, shall be at least 20 inches. So if we read the statement of this ACI code provision 18.8.2.3, it requires that this column dimension parallel to the beam reinforcement must be at least 20 times the diameter of the largest longitudinal bar. So if there are two types of the longitudinal bar being used in the beam, then the largest bar diameter shall be used in this, and the column dimension parallel to this bar shall be at least 20 times this. So, for example, if you want to design a frame structure, in the beginning you should make sure that you select sizes of the column such that they are 20 times of the anticipated bar diameter in the beam. Otherwise, you will have to change the column dimension at the end of your design. This is another provision for the exterior connection, exterior joint. In the exterior joint, the beam reinforcement both on the top and bottom side of the beam shall be carried to the far end of the joint in the column, and then the bars shall be properly hooked. And the length of the bar with the hook shall be at least equal to the LDH requirement of the code, which is FYDB 65 divided by C prime. So if this LDH criteria is not fulfilled, again you will have to increase the size of the column. These were the requirements for SMRF. Now we will quickly go through the IMRF, because IMRF is not difficult. IMRF you compared with SMRF, and some of the requirements are different. If there are no requirements, we will say that there are no special requirements. However, if there are some requirements, we will study all those requirements. So for the flexure members or beams, if a beam is part of IMRF, then there are no special requirement. Beam can be used of any size against the special moment reinforcement, against the SMRF requirements. In the SMRF requirement, if a beam is part of SMRF, then you have seen that there were a few requirements on the size of the beam. However, if a beam is part of IMRF, there is no special requirement. Flexure reinforcement are less stringent as compared to the SMRF. That will be discussed in the next slides. Transverse reinforcement, however, the requirements for transverse reinforcement are the same as for SMRF. And for lap, there are no special requirement, which means that lapping can be done at any location in the beam as well as in the beam. Sorry. Okay, these are the requirements for the reinforcement. That unlike SMRF, the area of steel on the bottom side at the ends of the beam should be at least 1/3 of the top reinforcement, unlike SMRF, where this requirement was 50%. Okay. And at any location, the maximum area of steel, at any location, the area of steel shall be equal to maximum area of steel divided by 5, 20% instead of 25%. Okay. Provision for columns. There are again no provisions for columns on size with respect to size. Flexure reinforcement, no special requirement, just as ordinary column requirement, 1% to 8%. Transverse reinforcement are less stringent, requirement is given next. And lap, no special requirement, just as ordinary column requirement. Provision for columns, this spacing L0, the length L0 is the same, however, the spacing is equal to 8 into smaller long bar diameter instead of 6, 24, and instead of 0.25, 0.5, and 12 inch. So these are less requirement. Okay. These were the requirements for spatial multi-string frame and intermediate multi-string frame. We have covered both of them. There are no special requirements for OMRF. At the end of the presentation, there are two requirements which although we discussed in the beginning, but we will reiterate those two requirements. That IMRF are not allowed in high seismic zones. However, SMRF are allowed in moderate seismic zones. Two-way slab system without beams are not allowed in zone 3 and 4. However, they are allowed in zone 2A and 2B. Next, we will study one example. But if you have any question, you can ask your questions. Otherwise, we'll go through this example before we take a break. And after the break, we will try to start our new lecture on the pre-stress concrete, which is a very easy lecture. So if you have any questions, you can just tell me your name and you can ask questions before we proceed with this example. This example will basically provides you an opportunity to understand the provisions of the ACI code and the use of these provisions, how these provisions are used in a practical example. Okay, so if there are no questions, let's start this example. The statement of this example is that there is a two-dimensional frame of the building, which is shown in the next figure. All beams in the frame are 12 inch wide and 18 inch deep. All columns are 12 inch square. It is required only for frame BFGC because this is a big frame. So only for a small part of the frame, this is required to provide suitable number of bars in beams and columns for which flexure reinforcement is shown in the figure. And we have to use only number 5 bar as main reinforcement, number 3 bar is transverse reinforcement. We have to provide suitable space. This example is being taken from one of the examination questions that was placed in one of the papers. Okay, so if we are able to solve this example, so then it will help you to solve questions in the examination. Okay, so the language of the question is just like an examination question instead of a design example. Okay, there is a frame, and we have to provide suitable number of bars in beams and columns for which suitable reinforcement, flexure reinforcement is shown in the figure. We have to use only number 5 bars for flexure, and number 3 bar is transverse reinforcement. Further, we have to provide suitable spacing for struts and ties when shear reinforcement is per design is 0.23 square inch per foot in all parts of the frame. And we have to satisfy all SMRF requirement for beams and columns as per code. And finally, we have to present appropriately proportioned structural details of beams and column, and we have to draw the beam column joint text as shown in figure 1. Okay, first of all, let's see how is this frame. This frame is like this. This is the frame. So this frame is taken from this part, the front part of this building. It will look like this in a two-dimensional frame. Okay, this frame has been analyzed and designed, and all the reinforcement obtained from the analysis are shown on this slide. Okay, let's say look at the BFGC frame, because if you look at the statement, so BFGC frame, this is BFGC frame, BFGC part. BFGC part of this frame is this BFGC part. We have to only look into this part, BFGC part. If you look at this this is column, and the longitudinal reinforcement obtained and given to us in the example is 3.2 square inch. This has been obtained from the analysis. Okay, analysis and design. And reinforcement in the beam on one side of the column is 3 square inch negative reinforcement, and positive reinforcement is 1.2 square inch. On the other side of the beam, this reinforcement is 2.6 and 1 square inch. Mid-span reinforcement is 1.8 square inch. On the other side of the beam, the same reinforcement was from the left. On the right of the beam at portion G, the same reinforcement is required. Okay, and the column CG also requires 3.2 square inch from the analysis. So these reinforcement, which are shown on the slide, has been obtained from the routine analysis design, with the only exception that this frame was part of this frame was subjected to lateral loading along with gravity load, and after the combination of bending moment from the gravity and earthquake loading, the reinforcement has been calculated against the combined effect of gravity and lateral loading. Okay, so this reinforcement have been obtained from the bending moments, and those bending moments were obtained from the analysis when the frame was subjected to gravity as well as lateral loading. Once these reinforcements are obtained, then we will have to check one by one the SMRF requirements. Now, what is required in the example? Number one, what is required in the example is that provide suitable number of bars in beams and columns for which reinforcement is required. So the reinforcement is here. We will provide number of bars. For columns, this is 3.2 square inch, 3.2 square inch. So we will use number 5 bars and calculate the number of bars. For beams, 3 square inch is the maximum reinforcement at the end of the beam, on top side of the beam, and on the positive side of the beam, the reinforcement is 1.2 square inch. Mid span reinforcement is 1.8 square inch. Okay, so let's say now calculate the number of bars. For the beam in the given figure, we have AS minimum is equal to 0.005, 0.9 square inch, and AS maximum is equal to 4.5 square inch. Negative reinforcement at the ends and positive reinforcement at mid span must be greater than AS minimum, and reinforcement at all location must be less than AS max. This is okay for the values on the given beam. And for the column, we have AS minimum is equal to 1.44. This is also okay. Now to calculate the number of bars. Negative reinforcement at joint. We have 3 square inch reinforcement, so 3 divided by 0.31 is equal to 9.67. We will round this up, and we will take 10 bars in 2 layers, and take 10 bars at joint for beam FG. So 10 bars will be placed here, 10 bars will be placed here. In 2 layers, 5 plus 5 bars. Positive bars mid span, 1.8 square inch, 1.8 divided by 0.31, 5.8 bars. We will use 6 bars in 2 layers, 4 plus 2 bars. 4 plus 2 bar is bottom reinforcement. Now at the end of the beam, 1.2. 1.2 divided by 0.31 is equal to 3.86. We will use 4 bars in 1 layer here at the end of the beam. Column reinforcement is 3.2 divided by 0.31, 10.32. But since it is a square column, so we can use the number of bars, which are multiple of 4. So we will use 12 bars instead of 11 bars, so that they can be evenly distributed on all faces of the column. This will be 5 plus 5 number 5 bar on this side, 4 plus 2 number 5, 4 number 5, 4 number 5, 12 number 5. This is the flexure reinforcement, and part 1 of this example is covered. Okay. Now, for the stirrup reinforcement, the statement in the example says that 0.23 square inch per foot reinforcement is required as per analysis with both beams and columns. We'll first look at the beams. The spacing from this reinforcement, 0.23 square inch, is, if we use number 3 two-leg vertical strip, so the area of bar is equal to 0.22 square inch. So 0.22 divided by 0.23 into 12. This spacing requirement is 11.47 inch center to center. From the gravity load requirement, you know, AVFY divided by 50 BWD by 2 and 24 inch. In this, the minimum reinforcement spacing, the minimum stirrup spacing comes out to be 7.5 inch center to center. This spacing shall be now checked against the requirement of the SMRF in the next slides. Okay, the tie spacing for the column for the gravity load is 16, diameter of the bar, you know, 48, and the spacing from the analysis is 11.47 inch. So the spacing requirement from the gravity load in the beam is 7.5 inch into center, and for the column is 10 inch into center. This reinforcement spacing shall be now, this transverse reinforcement spacing shall be checked against the special provision for SMRF. Now, the special provision for SMRF will be started in such a manner that sizes of the beam will be checked first. So the length and depth of the beam, we know 15 is the length of the beam, clear length, and effective D is 15. So 15 multiplied by 12 is 12. 12 is greater than 4. The size of the beam is okay. Width to depth ratio 12 divided by 18 is 0.67, greater than, so this is also okay. Width of the beam is 12 inch, which is greater than 10. So the size requirements are satisfied. The flexure reinforcement shall be checked against the provision of the ACI code. The maximum negative reinforcement from the analysis comes out to be 5 plus 5 number 5 bars. And from the analysis for the midspan is 4 plus 2 number 5 bar. And from the analysis on the bottom side is 4 number 5 bars. If you look at these bars, these are 10 bars, 5 plus 5, and here we have 4 bars. If you remember the requirement of the ACI code for beams, which are part of special multi-string frame, the bars here must be 5 bars. Okay, so these bars are less than 5 bars. We have to increase these 4 bars to 5 bars so that the SMRF requirements are fulfilled. Okay, we will do it like this. Area of steel edge joints must be greater than half of the area of steel joints. 4 number 5 bars are less than half of bars used on the negative side, so we have to provide at least 5 bars at joint. At any other section, 10 divided by 4. 10 divided by 4 bars, 2.5, but we'll provide at least 3 bars. So this requirement shall be fulfilled, okay, in the detailing. And this can be done in this manner, that instead of curtailing the bars on the positive side, we will not curtail the bars. We will continue the 4 plus 2 bars. We will continue 4 plus 2 bars so that 6 bars are used at the midspan of the beam as well as at the ends of the beam. So by this, the SMRF provision will be satisfied. Okay. So if we take a section now, at the midspan, we will see 4 plus 2 bars as well as here 4 plus 2 bars, 5 plus 2 bars. So this provision of the ACI code for the flexure reinforcement is satisfied. Next, the requirement of the ACI code for the transverse reinforcement within the 2H region. The depth of the beam is 18 inch, so 2H is 36 inch. Within this 36 inch, the stereo spacing shall be 15 divided by 4, 8 into smallest longitudinal bar diameter, hoop bar diameter, and 12 inch. From this 3.75 inch is the least spacing. And if you remember, from the analysis, the spacing was 7.5 inch. So instead of 7.5 inch, within this location of 2H, we will use 3.75 inch spacing. Lapping will be avoided, shall be away from the mid span and also from the 2H in this location, and lapping shall be provided as per the requirement of the code, which is 50 diameter of the bar for grade 40 and 75. So this comes out to be 2.5 feet. So this lap length shall be at least 2.5 feet, and the strip spacing within this region shall be 3 point, because it was D by 4 or 4 inch. In D by 4 is D is 15 inch, so 15 divided by 4 is 3.75 inch. For columns, all columns are 12 inch square, which is equal to least required for SMRF. Flexure reinforcement, all columns are reinforced with 12 number 5 bars, which gives 2.5%. So this is also within the specified range. Okay, and within the L0 region, L0 region shall be calculated now. L0 is maximum larger of column, which is 12 inches. HC divided by 6. HC is clear height of the column from bottom of this beam to top of this beam, which is 9.25 feet. 9.25 divided by 6 is 18.5 inch and 18 inch. So 18.5 inch is the largest. So within this 18.5 inch on both sides of the column, top and bottom, both sides of the column, the spacing in the stirrup, the spacing of the ties shall be 12 by 4, which is H1 or H2 divided by 4. So it is 12 divided by 4. 6 into longer bar diameter, this is 3.75 inch. Okay, so we'll use 3 inch within this region with 3 inch of spacing. And spacing other than at origin will be list of 6 longer by diameter or 6 inch, which is again 3.75 inch, so 3.75 inch. Okay. Similarly, the lap shall be provided the mid height of the column, and the spacing shall be at least d by 4, which is 2.82 inch. And the lap splice length shall be, according to this requirement, is 2.5 feet. To prevent beam column joint cracking, ACI code requires that the column dimension parallel to the beam reinforcement be at least 20 times the diameter of the longitudinal bar. And the longitudinal bar is 5 by 8, so 20 divided by 5, 20 into 5 by 8 is 12.5 inch, and we have assumed the column 12 inch. So this column size shall be changed, and we have changed this column size from 12 inch to 13.5 inch. The beam joint X detail has been shown here. The strap spacing shall be continued in the joint. The strap spacing of the column within the enlarged region shall be continued in the joint, as per ACI code requirement. Final part of this example is presentation of appropriately proportioned structural details of the beam column and selected joint. In this part, structural drawings showing all calculated SMRF details you have been asked to draw. This has already been done in part C, along with each member beam and column SMRF sketches. However, in the examination, it is better to draw all drawings here in the part D. Part D is shown next. This is the complete final beam flexure as well as transverse reinforcement with the sections shown here. 4 plus 2 bars, 4, 5 plus 5 bars. This is the lap location. You see 5 plus 5 bars is top, 4 plus 2 bars is bottom reinforcement. Okay, in section BB, only 3 bars on the negative side is being continued. This is the column detailing. 12 number 5 bars with the spacing. Joint details. With this lecture ends. This was demonstration of the SMRF requirements, the ACI code. Okay, if you have any question, you can ask questions. Any question? Please, if you have any question, you can ask questions. Otherwise, we will take a break. Any question?
No, sir. Thank you.
Okay. Any question? In the previous lecture or this lecture, if you have any question, you can ask your questions. Okay, if there are no questions, then we will take a break of 15 minutes, and after that, we will just start the next lecture, and this lecture will not be completed today. In this week, this will be completed in the next week. And then we have 2 more lectures, one on the introduction to bridge engineering, and then the design of retaining walls. Okay, and hopefully both the lectures will be completed before the semester ends. Okay, thank you.